A very good morning to all of you. Today we are going to study one of the most difficult topic, and that is rotating frames. We know wherever there is rotation it is quite difficult, but it is interesting also. And what interests me here, that when you solve the equations, when you do the mathematics from the mathematics part, the equations that we observe, that equations that we get, they explain the physical world. So it is very interesting to see that how the mathematics is following or explaining the physical phenomena. So while you go through this lecture, try to appreciate that how our mathematics explains the physical world. So in our last class we started the chapter which is our non-inertial frame. So in the non-inertial frame, the first frame we studied was linearly accelerated frame. Linearly accelerated frame. Today we are going to study the rotating frames, which is the second one, because both are accelerated frames. So presently we will quickly revise the linearly accelerated frames, then the rotating frames, the mathematics, then the acceleration and fictitious forces, important points about Coriolis and centrifugal force, examples, problems and assignments. Now quickly revise what we have done in our last class, linearly accelerated frame. Here, as you see, there are two frames, S and S prime. S frame is fixed to the earth, which is the inertial frame. We consider here that as an inertial frame. And the frame S prime, that is x prime, y prime, that is moving with respect to x with a constant acceleration a. We know the observations, we have our observations, that is our coordinates, our velocity, acceleration and force in the S frame for an event, some event here. How will an observer in the accelerated frame, which is moving with a constant acceleration, will observe the same event? That is our goal actually. So we know things from here, S frame, we want to know what is the observation in S prime frame. Event actually is independent of any reference frame. So A prime is equal to A minus A, it's perfectly fine. F prime is equal to F minus MA. This is a very interesting result that we got. F prime, that means the force observed in the primed reference frame or primed frame is not equal to F observed in the inertial frame, but there is a term which we are getting minus MA. Now this term is arising not because of interaction between the bodies, but it is because of acceleration of the frame with respect to that body. And that is why this is known as fictitious force. So what we have seen, that in a non-inertial frame, when you are observing any event, now that event may be outside the frame, inside the frame. But in order to analyze it, we have to put a force minus MA, and then we can apply the Newton's second law of motion, that is F is equal to MA. These are the things I have written. Now these examples are very illustrative examples. It shows that what is this fictitious force. As you see, the train is moving, accelerating on this side, and this observer will observe a block which is on the platform P moving backward with an acceleration A. So this man, since he is in the accelerating frame, he will see himself as at rest. So he will see that this block is accelerating backward. How he can justify? He will put a force minus MA in a direction opposite to in which the train is accelerating. So he can justify it. As you see, they are totally out. This particular body is not in the frame, totally out. But still you have to apply pseudo force or fictitious force. Now these examples will help us to understand our rotational frames. Here there is a block lying on a frictionless surface, exactly the similar, but now the body is inside but not interacting with the accelerating frame. So this observer will see this block to be going backward with an acceleration a, so we have to put a force m into a in order to apply the Newton's laws of motion, or in order to justify oneself. Here the third case is a mixed case. These are the two pure cases. So pure cases will show that how the acceleration of the frame is giving rise to this fictitious force. The third case is a combination of the two. That means this particular ball or mass which is hanging from a string, by a string from the ceiling, here as you see the real force and the pseudo force or the fictitious force both are present. So here it is very clear, but here it is a mixed case. So now you have tension T and you have pseudo force or fictitious force m into a in the direction -2 in which the automobile is accelerating. So here in our mixed case it is an interesting case. Here we see both real force as well as the pseudo force. Now the real force is there in the inertial frame as well as in the non-inertial frame. So these three examples tell us or show us that what actually is this fictitious force. Now let us come to the rotating frame. Simple example. So this is the first example generally I take, and why I take this, because here most of the time when we study about the rotating frames, we feel that the object should be inside the rotating frame, but it is not necessary. Object can be outside the rotating frame as well. So here the object is outside. Now if the object is outside, this observer is rotating. This is a rotating frame with an omega, angular velocity omega. This person will see that this block is rotating in the negative omega, minus omega direction, because he will see himself as at rest, but he will see this particular block to be rotating in the opposite direction. Now, how can he justify its motion? Because the moment you see something rotating, obviously we know that there is a force towards the center. The net force towards the center provided by something, and that net force, the net resultant force, algebraic sum of all the forces, we call that as a centripetal force. It is not a force by itself, but it is the net resultant force of all the forces. So there should be a net force which will act towards the center. So that force should be your pseudo forces or fictitious force. Otherwise he cannot justify its motion. Now we will see later exactly the same example we will take up, and we will see what are the fictitious force we need to apply so that this person can justify the motion of this block. Now it is also interesting to note that the event or the body that we are observing, it can be outside just like this, it can be inside means interacting with the frame, sitting on the frame, or it can be around the frame. Okay, so there are three different types of cases. Now I have already uploaded before, I think in last 2 years back when I was teaching Y20. So all these different examples of Coriolis force and the centrifugal force I have uploaded in that lecture. I request you to see that after this lecture, because now we are doing the mathematics, and after doing the mathematics, after understanding the fictitious forces in the rotating frame, we are in a position to see that video where different examples are grouped under this, like outside, inside, around. So all the examples are together, many examples. So it will help you, or it will help us to understand the Coriolis and the centrifugal force, which are actually the fictitious forces in the rotating frame that we are going to study now. Good. So now let us see the mathematics part. So rotating frames of reference. Before just that, what I would like to tell you, that many books, they write rotating axis, all right, rotating axis. I avoid that because sometimes in the polar coordinates, if a body is moving in a circle, then the r theta coordinate is moving with the body. So it is also a rotating axis, but it is not a rotating frame, because there the observer is standing outside. I am measuring the theta with respect to x-axis. In fact, after this lecture, I would also like you to see the lecture which I again uploaded long time back. That is the comparison between r theta coordinate, that is the polar coordinates, which also rotates with the particle, and the rotating frames. They are basically different. But how they are different, how they are similar, there are a lot of things we need to see. So after this lecture, you are requested to see that lecture also in YouTube. Okay, so the rotating frames of reference, that is why I write rotating frames of reference instead of rotating axis, because here it is a frame, and there is a frame, with that the axis is fixed, and that axis is rotating with the frame. The observer is in the frame. So let us see. Here we take Earth as a rotating frame. So this is the Earth, and the axes which are fixed with the Earth is x prime, y prime and z prime. Earth is rotating with an angular velocity omega. So it is rotating about its z prime axis. That means z prime axis. X, y, z is the axis which is inertial frame. Okay. Now inertial frame is fixed to the distant stars. Both the axes are rotating about a common point O and along the z prime axis. So both the axes, they have a common point O, and they are rotating about a common z axis, that is z prime is common to both of them. Now we can make this figure little simplified. What I have done over here, this is your O. We have presently removed this z prime, and in a two-dimensional plane I would like to show you that this x, y, we can call this as S frame also. This is, let us write, I have not written, we can write it S frame, and this we can write as S prime frame. We can write it, no problem. So x, y is your inertial frame, and x prime, y prime is your rotating frame. That is rotating with an angular velocity omega, again about the same origin O and common z axis. Z axis, I am not showing over here. Okay. Now, what I want to do, what is our purpose actually? We have seen earlier cases that our purpose was that we know something in the inertial frame. Whatever, we start with inertial frame, that the coordinates or the vector, the position vector, and what is the corresponding quantity in the rotating frame or in the accelerated frame. So this is our purpose, that is our goal. Now as you see, what I want to tell you that this particular derivations is done differently in different books. There are a lot of ways people have done it. I was going through different books, websites, also your YouTube videos. One of the common way people have done is that they have taken R, suppose say the vector R, in the xy plane, that is in the S frame, inertial frame, and how you observe that R in x prime, y prime frame. Okay. Now, that derivation is little long and little more mathematical. It is because, as you see, x prime, y prime axis is rotating. And when you start the derivation of R, derivative of R, the component of R will be changing in x prime, y prime. Not only that, I prime, I cap prime and j cap prime, they are also rotating. So when you differentiate R to get the velocity, you have to differentiate the unit vectors as well. So it is a long derivation, quite a rigorous derivation, but it is a long derivation. Lot of mathematics is there, and you have to use an identity of the rotating vector, that is dA by dt is equal to omega cross A. So that identity is used. But it is a long derivation, quite a rigorous one. Presently, I am not going to that derivation because there is too much of mathematics over there, algebra is there. Our purpose is to study the physics, to get a feel of it. So more of intuition, more of reasoning, more of physics, physics-based derivation I like better. Kleppner has done a derivation. Kleppner has taken it in a geometrical, using geometry he has done it. It's good, it's short, but at the same time tricky. The one that I am following over here is, I have taken this derivation from a book, Intermediate Physics by Patrick Hamill. It is a nice book. Now, in that book, the things they have done is a little bit in a different way, and that I like it. It is very simple, and from the common reasoning, from the normal reasoning, we can feel about it. Actually, we can feel the things. Now, what he has done is that he has taken R not in the inertial frame, he has taken R initially in the rotating frame itself. And from the rotating frame, we are observing now in the inertial frame. That is easier because inertial frame is fixed. So, how I am seeing that vector? Okay. So, why I am telling you different methods, that it is interesting to see that the different methods, they give rise to the same results. But still, we should see that the same results we can get from different ways. Sometimes it is very interesting to see that the different methods giving rise to the same result. So we must know what are the different methods people follow. Okay. Now, here when we start the derivation, it is a very simple and straightforward derivation. The first concept that sometimes we feel little difficult to understand, that there is a R vector. There is a mass over M, and the position vector of this mass is vector R. I am showing it by yellow color. Now, this R vector, suppose say if I take it in the xy frame or x prime y prime frame, it is same in both the frames. It is same in both the frames. Whether you take R first here in x prime y prime frame or you take R in xy frame, they are same. How they are same? We can see that. Because the magnitude of R and the direction of R is constant. It is, I am observing it. Different axis or different coordinate system is just observing it. Now as you see, suppose say for explanation just now, suppose say I take R in the inertial frame, that is your S frame. Now this particular frame is rotating. At a particular time, I have to freeze it because I am not interested about the velocity of R. Now, I am only interested about the vector R. So let us freeze, and let us freeze when x is coinciding with x prime. Suppose say x prime coincides with x, and y prime coincides with y. So in both the axes I will see the same r. Now suppose say I take the axis x prime and y prime such that x prime coincides with the vector r. Then what will happen? I will know the magnitude of r as whatever the magnitude is there, that is r I cap prime, and the direction is only along x prime, isn't it? But well, I can say I cap prime, but my I cap prime is along this direction now. So my direction is defined because that is the direction of I prime, I cap prime. If it is in the intermediate position, any positions, the components of r will keep on changing. At the same time, the unit vector, that is your I cap prime and j cap prime, they are also changing. So they are, so at that time I am defining the angle of r with respect to x prime, which is actually at this angle. So as you can see, if you can think a little bit, you see that the vector r is same in both the coordinate system. That is s and s prime, in both r is same. Okay. So now let us come to the derivation part. So here this r vector is in the s prime frame or x prime rotating frame. Rotating frame I am considering r. So position vector is same position vector in both rotational frame as well as a inertial frame. Now suppose say the mass m is at rest. That means it is rest where? In the rotational frame. In the rotational frame, mass m is at rest. I am taking the mass m in the rotational frame, that is your x prime y prime frame, and the vector r, which is the position vector of mass m, that is also in the x prime y prime frame. Now the mass is at rest. So if the mass is at rest, dr dt, that is the dr dt rotational frame, is equal to 0. In the inertial frame, what I will see, if the mass is at rest in the x prime y prime frame and the x prime y prime frame is rotating with an angular velocity omega, so I will see in the xy frame, that is the inertial frame, that the mass is moving with omega. That is very natural. So dr by dt, dr vector by dt in the inertial frame is omega cross r. Angular velocity is omega, so the linear velocity will be omega cross r. R omega, that is what we know, omega cross r. Now mass m, the second case is mass m has velocity vr. Now it is not stationary, it has some velocity vr, linear velocity vr. So dr by dt in the rotational frame is vr. What will be the linear velocity here? Dr by dt inertial frame will be omega cross r because of the rotation plus vr vector. This is very natural because suppose a train is traveling and within the train another body is having a velocity, so we add up the two velocity, isn't it? That is what we have done over here. I hope this is clear to you. So dr by dt inertial, dr by dt inertial is equal to vr. Vr I can write as dr by dt rotational plus omega cross f, omega cross r. So this is a very important formula or identity. Dr by dt inertial is equal to dr dt rotational plus omega cross r. As you see, in all these places it is same r is coming, r vector is coming. So this particular expression or this particular formula is applicable for any vectors. So for any vectors we can find a relation of their derivative between the rotational frame and the inertial frame. So we can write as ddt, or we can remove ddt inertial is equal to ddt rotational plus omega cross. So that is known as operator form. So we can write in the operator form, and here we can write here any vector. So using this relation, now this particular formula that we are getting over here, that Kleppner method, we don't get this intermediate formula. It is very quick and short. Why I wanted this method is that this is an important expression. We should also know about it. It is not at all whatever our goal is, that is okay. But along with the goal, the byproduct of the goal is also important, because we are able to learn this particular expression, if new formula, that is how to relate the derivative of a vector in the inertial frame with that of the rotational frame. Okay. Now, one point is very, very important, because in order to understand this formula, one particular example again given in that book, from there I have taken, is very important, and that is why we need to spend some time. If I put a vector over here, we have to remember that this vector is same throughout. That means this is whatever I write over here, same vector I have to write, same vector I have to write. Now when I am telling it to you, it's okay, but while dealing with the problems, it will create a sometimes nuisance, and that is why this particular problem is very good. Now the full words or wordings of the problem, I cannot write it because of lack of space, but let me tell you what the problem is all about. Here there is a disc. Now this disc is a old record player, the player disc, gramophone disc. So it is a gramophone disc actually, and that is rotating with a angular velocity capital omega naught. And there is a bug over here. This bug is also having its motion relative to this, and its velocity is Vb, and that is tangential motion. That means it doesn't have a radial velocity. Tangentially its velocity is Vb at a distance r from the center. Now there are different questions. Now as you see that this disc is rotating, and this particular bug is also rotating within the disc. So the disc is rotating, the bug is also rotating with respect to the disc. With respect to the disc. Okay. So the final velocity, what will be the velocity observed from the inertial frame? So there are two ways one can do it. One can do it directly, because what is the final velocity is you add up the two velocity. Okay. So both way you can write. Velocity of the bug with respect to the room, otherwise you can use the same formula, that is your Vi, that is your Vi inertial, that is V inertial is V rotational plus omega cross R. That is what the formula is. Vi is equal to V rotational plus omega cross R. V inertial is equal to V rotational plus omega cross R. Now, if you apply this, you will get this result, omega b plus omega 0 r phi. Omega b means omega of this, that you can find out. Vb and r is given. So Vb is equal to r omega. So basically it is omega bt is Vb by r. So that velocity from the inertial frame, what is the velocity. R multiplied by the total angular velocity is the velocity that is observed in the inertial frame. Even without applying this formula, you can directly write. Part B is what is the acceleration according to the centripetal acceleration formula. That is the question is. Full question I am not able to write because of space problem. So if I know the omega, so obviously the acceleration, centripetal acceleration is omega square r. That is what it is, omega b plus omega 0 whole square into r minus r cap towards the center. Now the third part is very important. This is why the question I have written. Calculate acceleration as per formula above. That means you have to use this particular formula and calculate the acceleration. Now in this formula, as you have seen, that du by dt inertial is equal to du by dt rotational to omega cross u. U is same throughout. So du by dt inertial will give me the acceleration in the inertial frame, and that is what we want to calculate. So let us write. So this u I have taken as, for this particle, Vb into phi. This is Vb into in the direction phi cap. Now differentiate this du by dt rotational. I am trying to find out this quantity. Du by dt rotational. So u I have taken as Vb phi. So du by dt rotational is Vb d phi cap by dt. D phi cap by dt we have studied. So Vb minus phi dot r cap, and that is equal to Vb minus phi cap minus phi dot. Phi dot is the with respect to the rotating frame. So phi dot is omega b r cap. Now here I have, as you see, that I have put a bit cross. Why? Because this particular, whatever we are doing, it will not give the correct answer. Where is the mistake? As you see, u when I am writing u here, that is rotational. Here u, when I am writing this u, this u is u inertial. Alright? The first time I have written u inertial. So I have to do, and that is what I want to calculate, du inertial by dt. This is what I want to calculate. So this u is also u inertial, but what I have written, u is equal to Vb phi. That is wrong. Correct one is, I have to write u as omega b plus omega 0 r phi cap. That is my u. U, that means this is my u inertial. That is my u inertial. So I have to write this u as u inertial and not u rotational. So I am making a mistake over here, and that is what this formula teaches us, that whenever we are writing this u, that means here u inertial, this is u also inertial, here also u inertial. So this particular u is u inertial, but I started with u rotational, and there the mistake is. So this is a very important problem which shows how to use this formula carefully. So though it takes a little bit of time, but doesn't matter, understanding of this particular important operator form is quite important. Good. So now with this knowledge, whatever we have gained, that is in the operator form, inertial, rotational, the relation between the two, we are now in a position to study the acceleration part, that how the acceleration will in the inertial frame and then the rotational frame, and what is the relation between the two. So that is the next topic, and that is little bit difficult. Now I request you to have a glass of water and just relax for 2 or 3 minutes, and then with fresh energy we will start the most important topic, that is the fictitious forces, how they are coming, the Coriolis force and the centrifugal force, and the derivation part of it, the mathematics part of it. Now we come to the second part, and that is the most important part. Okay, that is the acceleration and fictitious forces in rotational frames. This expression, this formula we have already read, that is relating the any vector between the inertial frame and rotational frame. So d, suppose say if I write r, only r in this operator form. So dr by dt inertial is equal to dr vector by dt rotational plus omega cross r. R is same throughout, and we know that r in the inertial frame and r in the rotational frame are also same. So this is perfectly fine. Now dr by dt is the velocity of the particle with respect to the inertial frame. That is your vi. So vi is the velocity of the particle with respect to the inertial frame. dr by dt, dr vector by dt rotational is the velocity of the particle with respect to the rotating frame. So vr. So vi and vr. Okay. If we substitute over here, we get vi vector is equal to vr vector plus omega cross r. So this gives a relation between the velocity in the inertial frame and the velocity of the particle in the rotating frame, omega cross r. This is an important expression. Let us number it too. Now we come to the acceleration part. That is the most important and little bit difficult also. Okay, so acceleration ai, what I do in the same operator form, instead of r, now I put vi. Now as we have learned that we have to put same vi everywhere. So this is vi here also, vi. Okay. So same vi vector, vi vector, vi vector. Everywhere it is the same. So dvi by dt inertial, dvi by dt rotational plus omega cross vi. So same vi, same vi, same vi. Now the problem is this dvi by dt, it is something doesn't make sense, because I am in the rotational frame and I am differentiating the velocity of the inertial frame. dvi by dt, here it makes sense, dvi by dt inertial, but here it is dvi by dt rotational. It doesn't make sense. If I have to dv by dt, then the v should be actually in the rotating frame, isn't it? So what I do, that I changed vi to vr plus omega cross r. So that is what it is being done. ddt of vi is vr plus omega cross r in the rotational frame. Plus omega cross, again vi is vr plus omega cross r, vr plus omega cross r. Now you expand. So ddt vr, r means rotating frame, plus ddt of omega cross r, that means rotating frame, plus omega cross vr, plus omega cross r. Fine. dvr by dt is ar. dvr by dt in the rotating frame is ar. Now what is ar? ar is acceleration of the particle in rotating frame. It is not that in the radial direction, no. ar is the acceleration of the particle, net acceleration of the particle in the rotating frame. So this is important, ar. In the rotating frame, what is the net acceleration of the particle? Plus d of omega cross r. So first you differentiate d omega dt cross r plus omega outside dr by dt. That is in the rotational frame. Okay. Now here is when you write d omega by dt, as we have taken initially we started with the earth, but we can take it for any rotating frame. In these problems, in these kinds of problems, whenever we do of the rotating frame, we take omega as constant. Okay. So earth also omega is constant. Usually we take this omega as constant. So d omega by dt is 0 because omega is constant. But suppose say you are given a problem or you are solving a problem where omega is changing, At that time, mind it, you have to be very careful with this expression. This expression will not work, final one. You have to add this term. That is d omega by dt, whatever it is. So you have to, you write it alpha or whatever it is. So you have to add this term actually. Okay. So d omega by dt r multiplied by m, whatever for the force, that is known as Euler force or Euler equation, Euler force actually. So if omega is not constant, then you have to add this Euler force corresponding to this expression. Okay. So omega cross dr by dt. So dr by dt, this is Vr. Dr by dt is Vr. Velocity of the particle in rotating frame. Dr by dt r is the Vr, velocity of the particle in rotating frame. Plus omega cross Vr plus omega cross r. So this is the full equation. Now, if you remove this, this is 0. This is omega cross Vr plus omega cross Vr. So 2 omega cross Vr and omega cross r. Finally, you get AI. AI means acceleration of the particle in inertial frame is equal to AR. AR is acceleration of the particle in rotating frame plus 2 omega cross Vr, 2 omega cross Vr plus omega cross r. Now this is a very, very important equation. The equation relating the acceleration of a particle in the inertial frame, observed in the inertial frame. This is the acceleration of the particle in the rotating frame. So it is relating to 2, and these two terms are there. Now these two terms, if you find out, they are also dimension of acceleration. This is a very important equation, and we will talk about it, we will think about it separately. But as I feel that one has to think very deeply on this equation. Now, what I can do, I can take AR out, on the other side, AR, we can write in terms of AR. AI we can write as F by m, because AI means acceleration in the inertial frame, which actually is force by mass. So force, this force is actually in the inertial frame, the real force actually, F by m minus the same minus, I am just taking to the other side, minus 2 omega cross V minus omega cross R. This is AR, that is the acceleration of the particle in the rotating frame is given by this. So acceleration of the particle in the rotating frame is the force divided by mass, force observed in the inertial frame, that is real force, minus these two acceleration. Now more important is, when you multiply this by m, then you get MAR, or you multiply by this by m, MAR is equal to F minus 2m omega cross Vr minus m omega cross R. This equation is very, very important, because it is telling us that what is the force. MAR means the magnitude of the force in the non-inertial rotating frame, is equal to the force. Force means the real forces which is observed from the inertial frame. That means this particular force is there in the inertial frame as well as in the non-inertial frame. So real forces are there in both. This is F. F minus this expression minus this expression. Now this is also very, very important equation which we need to understand. So this force is a real force. This is in both the frames. This particular expression minus 2m omega cross Vr, this actually is known as Coriolis force. And minus m omega cross R is the centrifugal force. These two forces, they are, as you see, they are having dimensions of force, but they doesn't look like that. The look is very different. though mass is there, but the look is very different. We will discuss about it. These two expressions are together actually constitute the fictitious forces. They are known as fictitious forces. This is the Coriolis force including minus sign, and this is the centrifugal force. And this is what I have written over here, that this is the Coriolis force and this is the centrifugal force. Now, so I hope the derivation is still clear to you. This is the real force minus this expression minus this expression. So they are, what are they? This understanding is quite difficult. And for this, we all have to think deeply that what are these two extra terms they have come? What are these extra terms? From where they have come? Why they have come? All these questions you have to ask. Their dimensions are all fours, but what is the nature of this? How do they arise? So this is actually we are going to understand. So these are the questions you must ask yourself, that whatever I asked you. Now, understanding fictitious forces. Now this particular slide, I have thought about it, and whatever I felt, I am going to tell you. I don't know how much I will make sense to you, but if you feel, if you are with me, perfectly fine, and if you think that no, it doesn't make much sense to you, you can think your own way. But understanding and thinking is very important. The more you think, the more you understand, the more you observe, the more you understand. See, understanding the fictitious forces, we can understand in two ways actually. One is thinking on the particular expression, on the mathematical form that we have derived. At the same time, we have to see the examples. There are various examples in nature which are of Coriolis force as well as the centrifugal force. Now, as I told you before, that these examples vary. In the next lecture, lecture on the Coriolis force and the centrifugal force, I have included many such examples. Now, when you see these examples, they can be grouped into different categories. And that is what I have done there. So, one class is when the object is outside the frame. The first is the object is inside the frame. Most of the time, that is a common thinking that the object is basically inside the frame. And what is that I am observing? That is the first common type of problems. But that the object can be outside the frame as well. Or sometimes there is a motion which is going outside, but at the same time it is not outside. Intermediate cases are also there. So all the three cases if you see and try to understand that what this Coriolis force and the centrifugal force is. It is very interesting. More interesting is the part that whatever mathematics we derive, using that mathematics we can explain the observations of the Coriolis force and the observation of centrifugal force. So the beauty of mathematics you can appreciate. So let us write down the same equation once again. AI is equal to AR plus 2 omega cross VR plus omega cross R. Now this is acceleration equation. Now why I have written this equation is that what we observe that in the expression of the Coriolis force, these two expressions, that means the acceleration terms which are coming over here, after getting multiplied by m, and when they go out on the other side, they are becoming the fictitious forces, as you see over here. So these accelerations over here are real, because it is in the inertial frame I am observing these accelerations. But they are little separate because I am writing AR. AR is acceleration of the particle in rotating frame. That is AR. But suddenly then two extra terms are coming. And these two extra terms, when they are multiplied by m and they go to the other side, this is what it is happening. They are becoming the fictitious forces. That is your Coriolis and centrifugal. So, if I want to understand the Coriolis and the centrifugal, we have to see what is their origin, from where they have come. So, they have come over from here. And as you see in the inertial frame, these are two accelerations which are real, because inertial frame, I am observing it from the inertial frame. Okay, so that is what I have written over here, that there are two terms over here. One is the Coriolis acceleration we call, and other is the centripetal acceleration. So we have to understand them, that what actually are they, because they are the one, they are becoming the, they are going to the other side, becoming negative multiplied by m, and they are becoming the Coriolis and fictitious centrifugal force. I have taken some two examples, and with my own understanding, I have tried to think about it and explain to you and share with you. But it's up to you. If you feel I am making sense, it's good. Otherwise, you can just delete this and think of your own way. Because, see, one way is the mathematics. Because whenever you are trying to solve a problem, you can solve a problem by using the mathematical formulas. But the other thing is getting a feel of it, understanding that what actually is happening. That is something very different, and that gives you the joy and shows how power of mathematics is. See, these two terms, that is your Coriolis acceleration and centripetal acceleration, what is common in both of them? The common in both of them that we observe, that both of them contains omega. And what is omega? Omega is a rotation. Omega is a rotation, the angular velocity of the frame. So, the frame is rotating, and because of this rotation, just because of the frame that is rotating, there is some acceleration which is coming up. Say for example, because unless we take an example we cannot, but there are different kinds of example, as I told you, something object outside, inside, but let us take simplest example, a coin suppose say, or mass or a coin is kept over here, stationary. Okay. Now it is a stationary coin and this wheel is rotating. This coin is stationary with respect to the observer inside the frame. Now, a person outside, that is in the inertial frame, he will see that this coin is rotating. Though it is stationary with respect to this frame, but this coin is rotating. And when this coin is rotating, we know that whenever something is rotating, there must be a net resultant force acting towards the center to give that acceleration, because there is a centripetal acceleration. For that acceleration to happen, there must be a force, which we call as the net central force. The name that we give is centripetal force. But there is a real force, and what is that real force is that obviously there is an acceleration, and acceleration is centripetal acceleration, that is your omega square r. This is your centripetal acceleration. Okay? And the force associated with that is Fr. And what is that force? That is a frictional force. So the frictional force is giving the necessary centripetal force for the centripetal acceleration. So centripetal acceleration is omega square r. That is when the mass is at rest. So exactly the same thing that we see over here, omega cross r is omega square r. So this we can understand well from this particular example, different examples are different. From this particular example, coin is sitting inside and a observer outside from the inertial frame, he is observing an acceleration because it is rotating. Also there is a force, which is the frictional force. So that is what we get as a centrifugal acceleration. So this particular acceleration is arising purely because of the rotation of the frame. Rotation of the frame. If the frame stops, this acceleration stops. The force is there. The force, there is real force also. But it is arising purely because of the rotation of the frame. Now, let us come to the Coriolis acceleration. Now, this is a difficult part. Understanding Coriolis acceleration. In the Coriolis acceleration, what is happening is that you are observing omega cross VR. That means the frame is rotating. And in the rotating frame, if there is a movement, then the both of them couple together. Then they form another set of accelerations. How? Let us take a very simple case, the simplest case actually. Simplest case is, suppose there is a mass m over here, mass m, and this mass m is traveling outward. Outward means along the radial direction, not any other direction, radial direction. And that is why I say simplest case. So it is traveling towards outside, along the radial direction. Now, we have solved this kind of problem in the polar coordinates. Again, polar coordinates is not a rotating frame. Their axis is rotating with the body, but the observer is outside. So that is different. I can attach a rotating frame over here with the mass m, and I see that the mass m is going out, but at the same time this frame is rotating, so obviously there is a theta dot in this direction and there is a r dot because the velocity v is there. So in my polar coordinates, in my inertial frame, I will see that it will have an acceleration. And what will be that acceleration? Because we know the radial acceleration is r double dot minus r theta dot square. That is the radial part. Here it is going, r dot and theta dot. So basically in the theta cap part, we see that two are there. That is 2 r dot theta dot minus r theta dot square. So 2 r dot theta dot basically is there. So what is 2 r dot theta dot? 2 v omega. R dot is v and theta dot is omega. So 2 v omega theta cap. So a person in a rotating frame is, if he is going away in the radial direction, he will experience a acceleration in the theta cap direction, that is 2 v omega theta cap. Now, we have also read there that why this acceleration is coming. Because this vector, the v vector, the direction of the v vector, which we call at that time r cap, here also r cap is changing. So basically any unit vector, if its direction is changing, because of the changing direction there is an acceleration which will be in the perpendicular direction, that is your theta cap. That is 1 r dot theta dot. The second r dot theta dot is coming because as this man is going outward, its tangential velocity, what is tangential velocity? That is r omega. Since r is increasing, so r omega is increasing, that means tangential velocity is increasing. And that actually happens in this Coriolis force actually, or Coriolis acceleration. So the tangential velocity is increasing as this man is going outward. So because of that there is another acceleration, another term in, that is r dot theta dot. So we get 2 r dot theta dot. Now this 2 v omega, here also if you see, if your Vr is along this direction, you get 2 v omega. So from the Coriolis, from the polar coordinates that we have learned, fixing a r cap theta cap frame, that is a inertial frame, From there we can understand that this term in the inertial acceleration term, this term is derived very differently, but we can understand this term, that what actually is this term, it is because of that. Because of that means the r cap vector is changing and r omega tangential velocity is changing. So because of that we are getting an acceleration. That acceleration we see over here. So at least we understand this term Coriolis acceleration. We are calling this as a Coriolis acceleration. Is this clear? Okay. Now I have not taken a general case. The general case is that suppose say the man, instead of going radially outward, he goes in a direction this way, this direction, that is making some angle with the radial direction. Then it will have a component in both r cap and theta cap direction. R cap directions we have already done. Theta cap basically will be added with, it will give, theta cap will have some angular velocity. That will be added with this angular velocity. So this plus this will be the angular velocity. So anyway, again if you apply your r theta coordinate system or your polar coordinates, so one acceleration you will be getting from this term, other one in the vertical tangential direction you are getting a velocity, and from there you are getting a term which is the acceleration is omega square r. Omega is now different. That is your omega 1, suppose say this is omega 1 plus omega, capital Omega. So that whole square into r. So when you whole square it, you will get that same centripetal acceleration term, omega square r, you will get it. You will get Coriolis term also, and you will get one term which will be added to AR also. Okay. So, I am not going into all those details, but one can do it. It is a good exercise. I think, you can do it actually and see that actually it matches. So now we have understood both the centripetal acceleration and the Coriolis acceleration that we see over here, in our own way. Furthermore, what we also observe is that both these accelerations, they are arising because of the rotation of the frame. If the frame is not rotating, then nothing will happen. All these accelerations are not there. So, it is because of the rotation of the frame. Now, since this acceleration we are observing, that is your Coriolis acceleration and the centripetal acceleration from the inertial frame, both the places we see a force, real force from the inertial frame. So, this particular man or this particular body which is there in the rotating frame, the Coriolis acceleration will be provided by again a frictional force. Here also the centripetal acceleration will be provided by a frictional force. So that is what we observe in the inertial frame of reference. From the inertial frame of reference, we observe the acceleration, we observe a corresponding force which is giving rise to that acceleration. But this is not in all cases. If the case is outside the frame, this will not happen. Things will be different. But this is for a particular case we are trying to show and trying to understand that what these terms are. That is centripetal acceleration and Coriolis acceleration. They are becoming, on the other side when they will go, they will becoming the what? Fictitious forces. Now you see in the non-inertial frame, that means now the observer is inside the frame. Both the observer they are inside the frame. This is the Coriolis acceleration part, and this is the centripetal part. Now here you see what happens, that this man will observe the coin or the body at rest. But there is a real force Fr which was giving the centripetal acceleration. So that force is real. He cannot neglect the real force. But he observes that this particle is at rest. So he has to apply another force to make that force 0. So there is a centrifugal force exactly equal to that. Now as you see, exactly m omega square r, that is that term, negative of that he will apply. Okay? So from here we can get a feel that what actually is from the centripetal acceleration, which was the term observed from the inertial frame, now the same thing in the negative direction has become the centrifugal force. I will conclude later on, but before that let me talk about this one. Here, though there are a lot of forces, these two forces will be here anyway. So Fr and Fc are there. But the main thing that we want to study over here is that this red color is Fr. That is the force that we have seen in the inertial system. Because there is a Coriolis acceleration. Coriolis acceleration will be provided by the friction. So Fr. Now this man, he is observing that this particular body is moving with a uniform velocity v. And uniform velocity v, that means there is no force. So 0 force is acting. So Fr, a negative force has to come opposite to Fr. Okay. Now what is Fr? Fr is m into a. That was Coriolis acceleration. M into this. So negative of that will come. So exactly the same way, the negative of the Coriolis acceleration multiplied by that will come here as a F Coriolis. Okay. Obviously those two forces will be there. That is your frictional force giving rise to the centripetal acceleration, and centrifugal force also will be there, Fc. So this is a picture. It shows all the forces actually, all the 4 forces. So this is also an interesting problem in the exam also you may get, that from a non-inertial point of view, what are the different forces that are acting on a body which is moving radially outward. So forces will be there. This is your Coriolis, this is your frictional force giving rise to the Coriolis acceleration. Opposite to that is F Coriolis, this is your F Coriolis, which is your pseudo force. Fr is a frictional force giving rise to the centripetal acceleration. The negative of that is Fc, which is your centrifugal force cancelling this. So all the forces are cancelling each other, this cancelling this, this cancelling this, this cancelling this. So the man or the body over here is in equilibrium and it is moving with a constant velocity v. Okay. So F Coriolis is Fr 2m v omega. Fr is Fc is equal to m omega square r centrifugal force. Okay. Now, what is the final conclusion after all these I would like to say? The final conclusion from these examples, there are many other examples as I told you. From these examples, the final conclusion that we would like to say, or I would like to conclude is, again it is a matter of choice whether you accept my explanation. What I want to say is that these terms, that is your Coriolis acceleration and the centripetal acceleration, which we observe from the inertial frame, which is real acceleration, and multiplied by the force, also there is a force associated with it. These accelerations are arising because of the rotation of the frame. This is purely because of the rotation of the frame. This is along with the rotation, if there is a velocity in the frame, then or outside the frame, whatever, with respect to the frame actually. So there is an interaction between the rotating velocity and the velocity with respect to the frame. So both are interacting. So basically the first thing is omega is common in both, that is rotation of the frame. In that, one more term is there that is more complicated. So these forces, when they go on the other side, basically they are arising, these effects are arising because of the rotation of the frame. Now, I am now observing the frame from outside. When I am going inside the frame, obviously my frame velocity is 0. My frame velocity is 0. So whatever effect was observed because of the rotation of the frame, I have to nullify that effect. Because that effect was because of the rotation and also interaction between the movement with respect to the rotating frame and the rotating frame. Okay. So because of that, these effects have come. Now, when I am going into the frame, I see no velocity of the frame. So whatever effects that I observed, like the effect was acceleration towards this, and there was a force, frictional force towards this, I have to cancel it, so that I don't see that effect. Okay. Here also I am doing the same thing. But if you take an example of a body which is outside the rotating frame, it is again little different example. So there the things are little opposite. It is outside the frame. So in a way you think about it, because if I keep on explaining examples after examples, then it will take a long time. What we have to understand is that what actually is the fictitious forces, the Coriolis force and the centrifugal force, what is their origin, and what these terms matter, what is the origin of these terms and the related force associated with these terms. So these are the questions we have to ask, and we have to understand that it is purely coming out because of rotation and the relative movement of the body, and these effects are coming to because these effects we are trying to cancel it, and then the forces like Coriolis and the centrifugal are coming. But again, different examples, the things are different. So purely it is a matter of kinematics. Because of kinematics, because of rotation and also that movement, there is some kind of observation which we see in the rotating frame, and then we have to incorporate those things. We need to bring some other forces. Well, this is what I have thought about it. I would like you to think more and understand these forces. So, but the essence of it is that it is the effect of rotation. The effect of rotation, and how to incorporate that effect of rotation in the rotating frame. In the rotating frame, when I go, I am observing something in the inertial, but in the rotating frame I am going, how I am incorporating those effects. Okay, so now let us see some of the important points about the fictitious forces. Some important points about the fictitious forces. It's worth remembering them. A fictitious force is a consequence of acceleration of the coordinate system, purely a matter of kinematics. That is what I tried to explain to you. Centrifugal force arises purely because of the rotation of the frame. Purely because of the rotation. So even if the object is at rest, with respect to the rotating frame, centrifugal force is there. Centrifugal force is always there in the rotating frame. It always points away from the axis of rotation. Good. Coriolis force arises because of its motion with respect to the rotating frame. That also we discussed. The event to be viewed may be inside the rotating frame or outside in the inertial system. If the body is within the rotating frame, then the effect of Coriolis and centrifugal force appears to be quite real. That means if suppose Earth as a system, something is happening within the Earth, then it appears to be real. Okay. So it appears to be quite real from the rotating system as Foucault pendulum. Now in Jaipur, long time back, there was a Foucault pendulum in the science center, and we will see if it is there. We will go to visit that. So Foucault pendulum is a very interesting effect of Coriolis force. Polar winds, trade winds on the surface of the earth, etc. So these are the examples where we feel the effect of the Coriolis force, and we feel that it is real. Okay, so we do not have too much of space or time here. A separate lecture, I have made long time back, giving all these examples in detail. There are a lot of examples, and I have grouped them into different cases. Like, here the thing is just the opposite. As you see, the body is outside. Now, the inertial frame will see that body at rest, but this frame now will see it as rotating. Just the reverse case. So this example we started with, and it is a very, very interesting example. This is where you can understand the Coriolis force and the centrifugal force. They are not only when the body is on the rotating frame, but it is also there, and it should be applied even if the body is outside. So when the body is outside, it is purely not interacting with the frame, but I am in the rotating frame. The observer is in the rotating frame. What you will observe? So everything is frame dependent. Here it is frame dependent. So there is a man who is in the rotating frame. There is a block over here, coin or whatever, of mass m. So what will he observe? He will observe that he will not observe that he is rotating. He will observe that this coin or the block is rotating in the opposite direction. So it is plus omega, he will see it as minus omega. Now, when he will see it as a minus omega, obviously it is rotating. It is just the reverse of the first case actually. Now the inertial man will see it at rest, but this man, the observer in the rotating frame, he will see that rotating. But so how will he justify that? There need to be a net centripetal acceleration, or centripetal acceleration is there, centripetal force basically, which is giving rise to this centripetal acceleration for this man, for the observer. Okay, so how will he do it? Let us see. See how the equations that we have derived, how beautifully it is applicable everywhere. So here, as you see, as it is rotating at this point, suppose say. Now, this point, if you apply the centrifugal force, because I am in the observer is in the non-inertial rotating frame. So both these forces, that is your centrifugal as well as Coriolis, we have to apply. Now centrifugal force is minus m omega cross r. What is omega? Omega is the omega of the frame. One has to be very careful. Not omega of this person, omega of the frame. Omega cross r. Now omega is here. So omega cross r. So you just see how the things are. Omega. This is your omega and this is your r. So omega cross r. And again omega cross. So again if you do omega cross, omega is this side, omega cross. So it is this side. Now minus of that. So it is on this side. So m omega square r is on this side. That is your centrifugal force. And we know that centrifugal force is always away from the center of or from the axis of rotation. So it is m omega square r. Now if you calculate the Coriolis force, because this person as seen by him is rotating. So there is a, with respect to the frame, there is a velocity. With respect to, though the person is not in the frame but outside, but so what? There is a VR. VR is velocity of the particle with respect to the frame. So there is a velocity. And what is that velocity? that will be r omega, omega cross r omega. The magnitude r omega in this direction. So it is in this direction, the velocity is in this direction. This will be the velocity in this direction. This is your v. Or you can say this is your VR, that is your velocity of this particle with respect to that frame. Okay, this is your VR. So you calculate again minus 2m omega cross VR, that is your Coriolis force. Minus 2m omega cross v. You will see that you will get the magnitude as 2m omega square r in a direction inside, that is towards the inside, towards the radial direction. So the centrifugal is outside m omega square r and Coriolis force is outside 2m omega square r. Now as you see, the net resultant force is m omega square r inside. So now this person who is rotating, he justifies that yes, the particle is rotating and there is a net force which is m omega square r, and that is what we should know. We know that any particle rotating in a circular motion, the magnitude of the force is m omega square r, the magnitude of the centripetal force. So that is what we get, m omega square r. So he justifies. So the whole theory of our centrifugal force and Coriolis force is working fine. But here as you see, again, I must stress that here the example is just the opposite of the first one that we have discussed. The first one discussed is that the coin is inside the frame. Now the coin is outside the frame. Okay. So if the coin is outside, the inertial frame, from there I am observing it zero force. But here now this person, because of its movement, because of its motion, or because of its rotation, it is observing some effect. So he is adding up the forces again to explain that effect. So all we need to see, or all we need to see over here is that the Coriolis acceleration or the centripetal acceleration, correspondingly the Coriolis force and the centrifugal force, they are arising because of the rotation. Alright, example 2, it is often given in many places, or in the videos. If you see, some of the very interesting videos are there. You must go in the internet and see the videos on Coriolis force. So they will see a man, there are two men over here, one man throwing a ball onto the other. So what will happen, the moment a man is throwing the ball to the other, in this direction actually, so this is the direction in which he is throwing to this man, but there is a Coriolis force. The Coriolis force will be centrifugal, anyway will be there, but there is a Coriolis force which will act. And why it is acting actually, you can see that the moment the ball is thrown, here the ball is having the tangential velocity, that is your r omega, is less. So tangential velocity here is very less, as it is going above the air. But this man is having maximum tangential velocity. So he will cross it and he will see this ball going backward. Okay. And using our Coriolis expression, that is minus 2m omega cross Vr, exactly you will get the exact direction as well as magnitude also one can calculate and see. So this is the direction in which this man will see. Here the things will be opposite. This man, while it is throwing, here the tangential velocity is quite high of this ball, but here it is, this one is less. So he will see the ball in front of him actually. Okay. So this is how the deflection will be seen when two persons are throwing the ball onto the other. Exactly the same way, when there are the low pressure band and the high pressure band, the wind they are moving, they get a deflection in the earth. So all this can be explained using the Coriolis effect. It is all because of the relative motion. Okay. Now we have two problems. One problem is a solved problem from Kleppner, and another problem I will tell the history of that problem, but let me first read the problem from the Kleppner. It is a simple problem. Now again, what I request you, that after I read the problem, you make a pause and try to solve the problem by yourself. Okay, it is a simple problem. A bead slides without friction, on a rigid wire, rotating at constant angular speed omega. So it is rotating at constant angular speed omega. Find the force excited by the wire on the bead. So what is the force excited by the wire on the bead? This is the problem. So here as you see that there is a normal force, which is a real force, normal force. And there will be two other forces. What are the two other forces? One is centrifugal force from the non-inertial frame. So I am making the whole diagram from the non-inertial frame. So this is FBD in non-inertial frame. From rotating frame. Okay. Or frame of the body. F Coriolis, because it is moving in the non-inertial frame, it is moving. So if I consider a frame over here, in that it is moving. So obviously there will be Coriolis force, and you can calculate the Coriolis force minus 2m omega cross Vr. This is the direction of V. So you will get in this direction. You can calculate and satisfy yourself. So let us solve. Now the force equations. This is the force equations. So F centrifugal, obviously, it is in this frame. In this frame, he is not seeing any rotation. It is only the body is going outward. So F centrifugal is mr double dot. And on the other side there is no acceleration, because from the frame which is sitting on the particle, there is no acceleration along the tangential direction. So F minus F Coriolis, here I have written Coriolis, this is Coriolis, is equal to 0. Now F centrifugal is, we know, m omega square r. So substitute back over here, m r double dot minus m omega square r is equal to 0. So we get a differential equation, and the solution of this is r is equal to a e to the power of omega t plus b e to the power of minus omega t. Solution of this simple differential equation. So a and b one can find out from the initial constants. Now the other equation, n is equal to n minus f Coriolis is equal to 0. Coriolis double r, 1 r is good enough. N is equal to f Coriolis is equal to 2m r dot omega. 2m r dot omega. R dot is Vr. So that is 2m omega square, basically 1 omega you are getting from here. You differentiate r dot, r you have already got. From there you calculate r dot, so omega square into this. So initial conditions are required for A and B. So it is a simple problem to show you how to write the free body diagram in a rotating frame, and how to solve the problems. Okay. Now the last problem. Now the last problem is an assignment for you, and it is a very, very interesting problem. Now let me tell you the history of this problem. This problem was first designed by Professor H.C. Verma of IIT when he was in the IIT Kanpur. Now he is retired. And at that time, I was working as a visiting faculty in IIT Jodhpur. At that time, it was IIT Rajasthan. And I was working as a tutor, and he was the instructor. So he had set up this question in the midsem for the IIT Jodhpur students. It is a very, very interesting problem. If you can solve this problem, it will clear your concepts basically on centrifugal force as well as on the Coriolis force. It is a very important problem which I still preserve, and this problem was given to many times to the LNMIT students also in different exams, in different formats, and maybe I will also sometimes give you changing the problem here and there. So you must be very thorough with this problem and try it by yourself. So I have not given the answers, later on we can discuss. But try and think and try to do it yourself. A horizontal turntable of radius 5 meters, a horizontal turntable of radius 5 meters is rotating at a constant angular speed of 5 radian per second. It is rotating. Say anti-clockwise, with respect to the ground, So the ground, they have fixed a frame A, and the other on the turntable, that means another frame we are fixing on the turntable with origin at the center of the turntable and rotating with the turntable, called frame B. So there are two frames, one with the turntable, one fixed to the ground, that is A, and this is B. A mass of double I have written. A mass of 50 kg is now walking tangentially on the ring. Now somebody is walking on the ring of the turntable opposite to the direction of rotation of the turntable, clockwise, with angular speed of 3 radian per second with respect to frame A, that means ground frame. Find the total force on the man as seen by frame A, both magnitude and direction. Centrifugal force on the man from frame B, that is rotating frame, both magnitude and direction. Coriolis force on the man from frame B, both magnitude and direction. Total force on the man as seen by frame B, both magnitude and direction. If man is stationary with respect to the turntable, the total force on him as seen by frame B. So these are the 5 parts to this question. Very small, quickly you can do it, but it will clear your concepts. And that is why in the last lecture also, I told you, you form some questions, you frame some questions. Maybe you go to the internet, see some questions. The moment you get good questions, it will clear your concepts. And that is why I am very much grateful to Professor Verma that he had set a very nice problem of this type which clears our concepts. Okay. So good, we have finished the chapter on, mostly it is dealing with the fictitious forces in the rotating frame, and the centripetal acceleration and the Coriolis acceleration. Corresponding to that, we have learned centrifugal force and the Coriolis force. So we have learned about how these forces are. They are basically coming from these accelerations, obviously. But what are these accelerations? These accelerations are because of the rotation of the frame. Because if you see the first equation, AR is equal to AR. So already AR is there. AR is the acceleration in the rotating frame plus 2 extra terms. So what are these? These extra terms are coming because of the acceleration of the frame. Now, if the object is within the frame, you observe in a certain way. If the object is outside the frame, you observe in a certain way. So whatever effects you see, those effects are to be explained using the concepts of your centrifugal and Coriolis force. So Coriolis and centrifugal force, when you are adding them, you see the effect and you can explain the effect. So those two forces are to be put in when you are seeing the things, observing the things, doing some mathematical problem solving from the rotational axis, from the rotational frame. So this is actually a very, very important but a difficult topic, and I request you see this lecture once or twice, but more important is you think about it. You take different examples, you think about it, that what actually is the centrifugal force and what actually is the Coriolis force and how they are related to the acceleration. So after this, I will request you go and see more lectures. The first lecture is how this rotating frame is different than the rotating axis in the polar coordinates, r theta coordinate that you have studied. They are different actually, but still there is some kind of similarity between them. So that is one. The second one actually is about Coriolis and centrifugal force. So there are large number of examples I have discussed, grouped into different groups. So go through that and try to explain that you are able to understand each and every example from both inertial frame as well as the rotating frame. So that will clear your concepts. So this is a very difficult, one of the most difficult chapter where you need to give time and think about it, think about the different examples, see some different problems from the book and formulate your own questions. Thank you very much.